Good day. Today I am going to explain the brute force algorithm. Brute force algorithm is a computational method that solves problems by systematically evaluating every possible solutions within a defined search space. It relies on raw processing power rather than clever shortcuts, guaranteeing a correct answer if one exists, though often at high time and resource costs. This approach exhaustively checks all candidates without assumption or optimization. For instance, finding the maximum in an unsorted array involves scanning every element once. They are simple to implement but scale poorly for large inputs, like trying all password combinations in cryptography. Its common applications appear in cryptography, cracking weak keys, optimization or testing all permutations, and data analysis or scanning for patterns. Backtracking variants build solutions incrementally, abandoning invalid paths early. Despite inefficiency, they serve as benchmarks for refined methods.
The learning task is about understanding how brute force algorithm works in a real-life situation. In the given problem, a passport is locked inside a digital safe at home. The safe can only be opened using a pin with numbers from 0 to 9. There is only a limited amount of time before the flight, and there are no other ways to open the safe. The learning task shows how the brute force method works by trying all possible pin combinations until the correct one is found. The program starts from the first possible combination and continues one by one. Through the learning task, we learn that when the pin is longer, there are more possible combinations. This makes the safe so secure but also increases the time for it to be opened. The learning task also explains the strengths and weaknesses of brute force. One strength is that it guarantees a result because all combinations are tested. One weakness is that it is slow and uses a lot of time, especially when the pin has many digits. Overall, the learning tasks help us understand how brute force works and why it is used only when there are no other options.
Hello everyone, let's move on to the implementation of the brute force algorithm. This code basically generates every possible numerical sequence for a specified lock length. First, we will import necessary modules. The iter tools needed for generating combinations, string to access the digits, and time needed to measure the performance of our algorithm. Inside the brute force lock function, first, we start with the initializations of important variables. We define our characters 0 through 9, attempts, and guesses to store every combinations the algorithm generates. Once initialization is complete, the program records the start time and begins its timer. Moving on to the core of the algorithm, the for loop uses iter_products and traverses through the entire search space and generates all the possible combinations given a specified length. After loop, the program then prints a snippet of the possible combination. For brevity, it was limited to the first 8 combinations and the last. Now, let's try the program.
Okay, let's say we want to find a total number of combination for a two-digit pin. Let's first input our number of pins, which is 2, then run our program and wait for it to be finished. We have a total of 100 combination. What about for 3? Let's simply switch it to 3, then run it, and let's wait to it for it to finish. We have a 1000 number of combinations. What about for 5? Let's run it. We have 100,000 number of combination. Let's go for 7. Let's wait for it to finish. And now we have 10 million number of combinations. What about for 8? Let's try it. Let's wait for our program to finish. We have a total of 100 million of combinations. That is all how our brute force lock algorithm works.
As the length of the combination increases, so does the time it takes for the program to list all the possible outcomes. For example, we have a 10-digit pin we need to crack. We will wait for it to process. That usually takes time because basically a 10-digit number has 10 billion possible combinations. The computational effort required to exhaust all the possible combinations grow exponentially.